Let's talk about one of the most elegant and honestly one of the most troubling equations in all of physics. This is a story about a piece of pure mathematics, so profound that it didn't just describe our universe, it predicted an entirely new one, a mirror world, made of something called antimatter.
Now, you'd think a story like this would kick off with some big celebration, right? But no, this one starts with complete despair. It's 1928, and Werner Heisenberg, one of the absolute giants of quantum mechanics, hears about a new theory, and his reaction is to call it the saddest chapter in modern physics. He was so shaken, he literally considered just quitting physics altogether.
So what was it? What could possibly be so upsetting? What did this new theory predict that sent some of the most brilliant people on the planet into a total spiral? Well, to understand their panic, we've got to go back to the single biggest problem in physics at the time.
You see, physicists were staring down a massive contradiction. They had two incredible theories that described how the universe worked, but these two theories just wouldn't play nice. It was this epic quest to unite two completely different worlds.
On one side, you had Einstein's relativity. These were the rules for the really, really fast stuff, things moving close to the speed of light. And on the other side, you had Schrödinger's quantum mechanics, which laid out the bizarre rules for the really, really small stuff, like electrons. The problem: the two theories were totally incompatible. And look, this wasn't just some abstract problem on a blackboard. Schrödinger's equation, which was the absolute cornerstone of quantum mechanics, was making predictions that were just plain wrong. It predicted that gold should look like silver, and that mercury should be a solid. Why? Well, it's because in heavy atoms, those little electrons are whipping around so fast, they're actually approaching the speed of light, and Schrödinger's math just completely falls apart at those speeds. It wasn't relativistic. So the solution seems kinda obvious, right? Just build a new quantum equation, but this time use Einstein's relativistic formula for energy. And that's exactly what a couple of physicists, Oscar Klein and Walter Gordon, did. The result was called the Klein-Gordon equation, and it was the first real attempt to bridge that gap.
But there was a huge flaw, a fatal one, actually. The way the math was set up, the equation could spit out negative probabilities. Imagine someone tells you there's a negative 10% chance of rain tomorrow. What does that even mean? It makes no sense. As one physicist put it very bluntly, that, of course, is physically nonsense. And that physicist, well, he's about to become the hero of our story.
So, that first attempt was a total bust. The field needed someone new. Someone who wasn't just trying to make an equation that worked, but someone who was searching for an equation that was beautiful. So let's meet the man who would finally crack this puzzle, Paul Dirac.
Dirac was, he was a character. His colleagues called him the strangest man. They even invented a unit of measurement called the Dirac, which was basically 1 word per hour. That's how little he spoke. But his guiding principle, his core belief, was that the laws of nature had to be mathematically elegant. For him, beauty wasn't just a nice bonus, it was the ultimate signpost pointing toward the truth.
So Dirac looked at the Klein-Gordon equation and saw the problem right away. It treated time in this really messy, complicated way. He decided he was going to build something cleaner, more elegant. So he starts with Einstein's formula, but he insists that his new equation has to treat time on the exact same footing as space. But when he tried to solve for the math he needed, he hit a wall. Using regular, everyday numbers, the equations just wouldn't work. And the whole problem boiled down to this really strange but super important idea. Sometimes the order in which you do things completely changes the result, right? Think about it. Putting on your socks and then your shoes is very, very different from putting on your shoes and then trying to put on your socks. Dirac realized that whatever new math he needed, it had to have that exact property. And it just so happens there's a mathematical tool that's perfect for this. Matrices. These are basically just grids of numbers, but when you multiply them, they don't follow the simple rule that A times B is always the same as B times A. Just like with the socks and shoes, the order matters. Dirac's friend, Werner Heisenberg, had actually used them in quantum mechanics before, and Dirac knew this was it. This was what he needed.
Now, here's where things get really cool. Dirac first tried using simple 2x2 matrices, but he couldn't get them to work together. And then he had this incredible breakthrough. He later said, "I suddenly realized that there was no need to stick to 2 rows and columns. Why not go to 4? It was this amazing leap of pure mathematical intuition, all driven by his quest for elegance.
And with those 4x4 matrices, everything just clicked into place.
The result was the Dirac equation. It was shockingly simple, it was perfectly symmetrical, and it was just profoundly beautiful. He had found his masterpiece.
But this mathematical beauty came at a very steep price. The equation worked, absolutely, but it predicted something so bizarre, so seemingly impossible, that it threw the entire world of physics into complete and utter chaos.
Okay, but first, let's just take a second to appreciate everything it got right, because it was amazing. It was fully compatible with relativity. Check. It treated space and time as the single space-time that Einstein talked about. Check. And then, almost by accident, it predicted a weird property of electrons called spin, which perfectly explained experimental results that had been a total mystery before. This equation was undeniably powerful. So here's the crucial part. It all comes down to this number, 4. Because Dirac used 4x4 matrices, his equation didn't have just one solution to describe the electron. It had 4.
Now, 2 of those solutions made perfect sense. They corresponded to the electron's 2 different spin states. You could call them spin up and spin down. But that left a really haunting question. What on earth were the other 2 solutions describing?
And this was the answer that horrified everyone. The other 2 solutions described particles with negative energy. This is what made Heisenberg despair. I mean, a particle with negative energy is a disaster. It could just keep radiating photons forever, falling into this infinite abyss of negativity. It seemed to break the laws of reality itself.
So for 3 years, Dirac is defending his beautiful equation while all his colleagues are in a total panic. They all saw a fatal flaw. But Dirac, he trusted the elegance of the math. He saw a prophecy. He absolutely refused to believe the equation was wrong, and instead he made a truly revolutionary leap.
In 1931, he proposed something that sounded like science fiction. He said, what if these negative energy solutions aren't a mistake? What if they're a prediction? He theorized that for every single electron, there must exist an anti-electron, a particle with the exact same mass but the opposite positive charge. He was literally predicting a new kind of matter.
And what happened next is just proof of the sheer power of this idea. Just 1 year later, 1 year, a physicist named Carl Anderson is studying cosmic rays, and he takes a photograph of a particle track that behaves exactly like an electron, but it curves the opposite way in a magnetic field. It had to have a positive charge. He had completely by accident discovered Dirac's anti-electron. He called it the positron. Dirac's beautiful equation was right all along. His relentless search for mathematical elegance hadn't just united relativity and quantum mechanics, it had uncovered an entire mirror universe of antimatter. But in solving one great mystery, it created an even bigger one about our own universe.
See, according to everything we know, the Big Bang should have created equal amounts of matter and antimatter. In the superdense early universe, they should have immediately found each other and just annihilated into pure energy, leaving behind absolutely nothing. But, obviously, that's not what happened. We're here, you're here. So the ultimate question Dirac's equation leaves us with is this: why does anything exist at all? Why did matter win?